Data extracted from the real world is not clean, especially if it's derived from multiple sources. It is inconsistent, contains irrelevant information, and sometimes it's missing values. Therefore, it is important to clean such data before doing anything else. In this section, we'll learn some basic techniques to be able to clean our data and get it ready so we can use it for practical purposes and manipulate it. As I said earlier, the decisions we make depend upon the data that we have. Hence, the quality of our decisions is only as good as the quality of our data. If our data contains incorrect or irrelevant information, which quite often it does, our decision is going to be incorrect. Hence, there is a natural need for cleaning the data. There is no one definition of a high quality data, but generally, data is considered high quality if it is fit for its intended use in operations, decision making, and planning. We can also improve the quality of our data through different data cleaning techniques. An anomaly is an observation in the data that significantly differs from the rest of the data. It is also called an outlier. An anomaly indicates that there is something wrong in the data. For example, consider the series containing weights of the same table measured by 5 different students. 4 of the values are pretty close to each other, but the middle value, which is 4.5, is way bigger than the rest. This could indicate that the third student was very careless while measuring, or that the instrument they used was defected. In any case, the third value is an anomaly, since it is different than the standard pattern. Data extracted from real world often contains such anomalies, and it is important to detect and deal with them appropriately. For accurate results, let's have a look at some techniques to detect anomalies in the data. One way to detect anomalies is using the median value. We take the absolute difference between every value and the median. If for a certain value the difference is bigger than a reasonable threshold, we consider that value an anomaly. Let's now see in action how we can detect anomalies based on the median value. Alright, let's first create the series that we saw in the slides. X equals pd dot series, open brackets, open square brackets, 2.1, 2.2, 4.5, 2.2, 2.4, close all brackets. Okay, so we need to find the median value of the series and choose a threshold value. The threshold value depends on the data. Let's select a threshold value of 2 in this case. We will also create a list to hold outliers or anomalies. Okay, so I'll write median equals np.median brackets x. Threshold equals 2, outliers equals square brackets. Next, we will iterate over the series and compute the absolute difference between each value and the median value. If ABS, item minus median, is greater than threshold, the value is an outlier, and we'll add that to the list of outliers. For item in X, if ABS brackets item dash median, close brackets, forward arrow, threshold, outliers dot append brackets item. The abs brackets function is used to get the absolute value. Finally, we will print our list of outliers. Print brackets outliers. Click run, and as expected, the value 4.5 is an anomaly or an outlier. Here is a small quiz for you. 7 minus 3 is 4, which is greater than the threshold. Hence, 7 is an anomaly in the data. We can also detect anomalies using the mean and the standard deviation. We define the lower bound as mean minus standard deviation and the upper bound as mean plus standard deviation. Any value outside this range is considered an anomaly. Note that, depending on the data, sometimes you might want to define the lower bound as mean minus 2 times standard deviation, and the upper bound as mean plus 2 times standard deviation, or even bigger. Alright, let's now see how this works in Jupyter Notebook. In this example, we will detect anomalies in our data using mean and standard deviation. X equals pd.series, open both brackets, 2.1, 2.3, 4.5, 2.2, 2.4, close all brackets. Mean equals np dot mean brackets x. std equals np std brackets x. Outliers equals empty list. Next, we iterate over our data to see if any value of our data is less than the mean minus standard deviation or greater than the mean plus standard deviation. If it is, we append it to our outliers list. Alright, let me do this. For item in X, if items is less than mean minus STD, or item is greater than mean plus STD. Outliers dot append brackets item. Finally, let's print the outliers list. Remember, in Jupyter Notebook, we can print a variable just by writing its name. So I'm going to write outliers. Let's run this cell. And here you go. This method also returned the anomaly correctly. Let's test your knowledge with a quick question. The value is 16 is less than the lower bound, i.e. 17.5. Yet another method to detect anomalies in the data is the z-score, which is a statistical measure that shows how many standard deviations our value is from the mean value. If the z-score of a value is greater than a certain reasonable threshold, that value is treated as an outlier. Let's detect anomalies in our data using the z-score of the values. Alright, we have our data. We've computed its mean and standard deviation. X equals pd.series, open brackets, 2.1, 2.3, 4.5, 2.2, 2.4, close all brackets. Mean equals np.mean brackets x, std equals np.std brackets x, outliers equals close square brackets. Now we'll iterate over the data and compute the z-score of every value. Z-score is computed by subtracting the mean from the value and dividing the result by the standard deviation. We will set the threshold to 1.5, which means that any value that is more than 1.5 standard deviations away from the mean is regarded as an anomaly. Okay, so let me write for item in X, z underscore score equals brackets item minus mean close brackets divided by std if z underscore score is greater than 1.5. Outliers dot append brackets item, print brackets outliers. Let's run this cell to see the output. Once again, 4.5 is the outlier or anomaly in our data, which means that this value is more than 1.5 standard deviation away from the mean value. A certain data set has a mean value of 12 and a standard deviation of 2. A certain value x in the dataset is 8. Compute the z-score of the value x. The correct answer is 2. Interquartile range is another way to detect anomalies in the data. A quartile divides the sorted data into 3 points and 4 intervals. The first quartile is at 25%, the second at 50%, or the median, and the third quartile is at 75%. The difference between the third and the first quartile is called the interquartile range and is an effective metric to detect anomaly in the data. Consider the given list of weights. In order to compute the quartiles, we first need to sort the data from smallest to largest value, which is the second list that you see on the screen. Now, first quartile, also known as Q1, is the value at 25% of the data, which is 2.2. The second quartile, also known as Q2, is the value at 50% of the data, which also happens to be the median of the dataset. In this case, Q2 is 2.3. Finally, the third quartile, or Q3, is the value at 75%, which is in this case is 2.5. The interquartile range is the difference between Q3 and Q1. We can compute quartiles in Python using the percentile brackets function available inside the NumPy library, which also sorts the data automatically before computing the quartiles. Any value in the data that is less than Q1 minus 1.5 times IQR or bigger than Q3 plus 1.5 times IQR is regarded as an anomaly. Let's now compute the interquartile range of our data. For this, we will use the numpy.percentile brackets function, which takes data at a list containing the quartile percentages. Since we want the first and the third quartiles, we will pass a list containing 25 and 75 respectively to the function we mentioned. So I'll need to write x equals pd.serieses open brackets 2.1, 2.3, 4.5, 2.2, 2.5 close brackets q1, q3 equals np.percentile bracket x, open square brackets 25, 75 close all brackets IQR equals Q3 minus Q1 outliers equals square brackets. Next, we iterate the data to check if any value is outside the range that we defined in the slides. For item in X, if item is less than brackets Q1 minus 1.5 multiply IQR close brackets, or item is greater than brackets Q3 plus 1.5 multiply IQR close brackets, outliers dot append brackets item outliers. Click run, and again 4.5 is the outlier or anomaly in our data based on interquartile range as well. In all the methods for anomaly detection, we got the same result. However, this is not always the case. Time for another quiz. Remember that first quartile is the value of 25% of the dataset, second quartile is the median value, and the third quartile is the value at 75% of the dataset. Here is the correct answer. I hope you got it right. Another major part of data cleaning is dealing with the missing values in the data. Let's take, for example, a dataset that contains stock information including their prices. Suppose that the price of a certain stock at a certain date is missing because the stock was delisted. Depending on what you intend to do with the data, you might want to delete that row completely from the dataset or fill the missing value with an appropriate value. Consider the dataset in this figure. The age of James is missing. Pandas represents the missing value as nan, which is short for not a number. In large datasets, it's not convenient to manually search for columns containing missing values. The .InsNull function gives a true for cells where there is a null value or missing value, and a false otherwise. We can use the .sum function combined with the .isNull function to find the total number of missing values in each column. Let's see how this works in the Jupyter Notebook. Our data frame is called data and contains two columns, name and age, as shown in the slides. Let's see what .isNull gives us. Data.isNull click run. We get a data frame and we can see that the third row of the second column contains a true because there is a missing value in the dataset. Now let's combine .isNull with the .sum function. Data.isNull Run this cell. So, our name column contains 0 missing values, and our age column contains 1 missing value, just as we expected. As mentioned earlier, we can either completely remove the rows containing missing values or fill in missing values with some appropriate values, such as mean, median, or mode of the entire column. The method to use depends upon what you want to do with the data, but generally speaking, if there are a few missing values, we can delete the rows containing those values. However, if there are a lot of such values, deleting rows would result in a significant loss of information. In such cases, gathering more data and filling the missing values with the statistical measures such as the mean, median, or mode could be a better option. Let's see how we can remove rows containing missing values. So, to delete rows containing missing values from the dataset, use the .dropNa function. Don't forget to set in place equals true. Data.dropNa in place equals true close brackets. Data. Click run. The row with the label 2 has been deleted since it contained a missing value from the age column. We can also replace missing values in every column with the mean, median, or mode of the respective columns using the .fillNa function. Let's see how we can replace missing values with the mean values. Let's replace the missing values in every column of our data by the mean of the respective column. It is very easy in Panda using the .fillNa method, which automatically fills the missing values of every column by the mean of the respective column. Data.fillNa data.mean comma in place equals true close brackets data. Remember, the age of the James was missing. Let's see what happens when we run this cell. Click run, and here you go. The missing values have been replaced by the mean of the age column. We can also replace missing values of a column by the mode of the column using the .fillNA brackets method. Let's see how. In this tutorial, we will replace the missing value in the age column of our dataset that we saw in the slides with the mode of the age column. Notice that our data column has now one additional row containing Stuart and 27. Let's start by computing the mode of the age column. Data, open square brackets, age, close square brackets, dot mode brackets. Click Run. The mode is 27.0. Now, let's fill the missing value with this mode. Data, square brackets, age, dot fill NA, brackets, data, square brackets, age, dot mode, brackets, 0, comma, in place equals true, close bracket, data. We run this cell, and the missing value has now been replaced with the mode, which is 27. Regular expressions are used to match patterns in a string. They are used widely in data cleaning and for other purposes as well, such as finding telephone numbers in a string, etc. We can use regular expression in Python using the RE module. The RE.findAll brackets function finds all occurrences of matches in a string. The first parameter of the function is the pattern to match, and the second parameter is the string in which the pattern is to be found. Let's see an example in Jupyter Notebook. Let's start with importing the RE module. Import RE. Next, we will create a string and find all the occurrences of Python in the string. txt equals Python is my favorite programming language. I love Python. X equals re.findAll brackets Python, comma, txt, close brackets, x. Click Run. We get a list containing Python twice. Let's now use the .len brackets function to find the length of the list x. Len brackets x. Execute the cell, and as expected, we get 2. So the word Python appears twice in our string. To check if a string starts with a certain pattern, we can use the hat symbol before the pattern. A match exists only if the string starts with the pattern after the hat symbol. In the given figure, since the string x starts with the word Python, we get a list which indicates a match. In the case of the string y, it does not start with the word Python, and hence we get an empty list indicating no match. There are some built-in sequences to match certain patterns. For example, to match numbers, use the \d sequence which matches sequences. Add a plus sign at the end of the \d to match more than one occurrence. Let's see how we can find digits in a string. Let's create a string and find digits using the \d sequence. txt equals Python was released in 1991. re.findAll brackets \d, txt, close brackets. Let's run this cell. So we do get all the digits in the string, but individually. We would like to get a 1991 as a single number. We can add the plus sign at the end of the \d sequence to match more than one occurrence. This would make sure that we get 1991 as a single number. txt equals Python was released in 1991. re.findAll brackets \d plus, comma, txt, close brackets. Execute the cell and we get what we wanted. Regular expressions in Python work on strings. To make them work on a series of a data frame, we can convert the series to strings using the built-in .to_string brackets function. Another function in the RE module is the .search brackets function, which returns a match object only if there is a pattern match. We can find the position of the match using the .span brackets function of the match object. Let's start with creating a string hello world. We will first check if the word world exists in the string or not, using the re.search brackets function. If the re.search returns a match object, it means that there is a match. txt equals hello world match underscore object equals re.search brackets world comma txt close brackets match underscore object. Run this cell and we get a match object as shown in the figure, indicating that the word world exists in our string. Let's find its position. Match underscore objects dot span brackets. Execute this cell and we can see that the word world begins at position 6. RE model has another useful method, the re.sub brackets method, to substitute a text in a string with another text. In this tutorial, we will create a string and then use the re.sub brackets method to replace the existing text with a new text. txt equals C is my favorite programming language. Let's replace C with the Python word. The first parameter in the function is the text to be replaced. Second parameter is the text to replace with. And the third parameter is the string. re.sub brackets pattern equals C, comma, repl equals Python, comma, string equals text, close brackets. Click Run to execute the cell. And as you can see, C is now replaced with Python. If you'd like to practice regular expressions, check out regex101.com. It is a free website to create and text regex with ease. This section now comes to an end. We hope you enjoyed it as much as we did. Here are a few resources for you if you would like to learn more. See you soon. A column of a dataset is also called a feature or attribute. Different features will have different ranges of values. For example, as shown in the figure, the age column is in the range 1 to 100 and the salary is in the range of thousands. Sometimes we might want all or some of the features to be in the same range. This can be achieved with feature scaling. One way to scale the features is normalization, or the min equals max scaling, which scales the features in the range square brackets 0 to 1. From each value of the feature, we subtract the minimal value of the feature and divide the result by the difference of minimum and maximum values of the same feature. Feature scaling in Pandas is very easy and can be done without the for loops. Let's see how. This is our dataset from the previous slides. df. We will perform min-max scaling on both columns. df equals brackets df minus df dot min close brackets / brackets df dot max brackets minus df dot min close brackets df. Let's run this cell to see the output. Great! Both columns are now in the 0 to 1 range. We can also scale the features through standardization, in which we subtract the mean of a feature from each value in that feature, and then we divide the result by the standard deviation of the feature. Resultantly, the standard deviation of the feature becomes 1. Standardization is also very easy to implement in Panda. Let's try it in Jupyter Notebook. In this tutorial, we will standardize all the columns of our data frame used in previous slides. df, we run this cell. So, this is df. Okay, so let's do the feature scaling. df equals brackets df minus df dot mean close brackets / df dot std brackets df. Click run. Both columns have been standardized. Let's now see what the standard deviation of the two features is. df dot std brackets. Run this cell. The standard deviation of both features is 1, as we discussed. Great! Which feature's scaling method is also known as min-max scaling? The correct answer is normalization.